Yes.
Okay.
You got online class now?
Okay, good morning. Any questions? No question? Everything's good?
What
Nah,
the best
what-
part
what we gonna be doing in this class?
Huh?
What we gonna be doing?
You
Like
missed the
315?
316.
I'm saying just like 315?
No, only the first chapter. Modulation, demodulation.
Okay.
You missed the first time. Check the syllabus. Everything is in the syllabus. Alright? Last time we discussed up to the orthogonal functions. So we know all the harmonic functions are harmonic. Yes.
So the notes online, right?
The notes is not
So-
online, so you need to write the notes here if you want.
Oh man.
Huh?
Sure.
Pay more attention. So, for example, sin mx times and sin nx, that one equals the integration and the x that will be equal to 1 if m equals n. If m not equals n, then that one will be equal to 0. So that is from 0 to t, 1 over t. So that means these two are orthogonal. Orthogonal means the integration within some range divided by the length of the range will be equal to 0. Next one, we are going to discuss signals in time domain. Vt equals v e to the j omega t plus 0. And this one can be represented by this is exponential form. And we can represent this in real part and imaginary part. So that's going to be cosine omega t plus theta, then plus j v0 sin omega t plus omega theta. And so if you are given, for example, the input, if the input is like v t equals cosine omega t, then what we do is we can assume that one is just so v0, and that one we assume the input is exponential like this, but we are going to take the real part. This is useful. Why? Because later time, if we look, the input is a cosine function, then we can still assume the input is exponential. But at the last step, we just take the real part of the solution, then that will be the output of the real system. For example, when we analyze the bandwidth of FM signal, later time we are going to discuss this. We are going to use this technique. Phasor representation. The voltage will be equal to, in this case, V0 and with the angle. Here we do not need to consider the frequency. The reason is we deal with only linear circuit. Linear circuit, there's no new frequency generated. So all the frequencies are the same. The input frequency equals the output frequency. So we can ignore the frequency. The next topic is signals in frequency domain. For example, we are given this signal. We know the frequency equals omega. So if we observe this signal on oscilloscope, the signal looks like a sine function or cosine function look like this. But how about if we observe this signal with a spectrum analyzer? That means we look at the frequency component. So the frequency component here we know this is a singular frequency. There's only one frequency, and the amplitude equals V0. So if we look at this on the spectrum analyzer, it will look like this. So this is 0, and the frequency is here, omega, and the amplitude will be equal to V0. And we can represent this mathematically as We know this from ET323, right? So this one can be represented by impulse. So this one here, impulse T, we use omega, right? So this omega 0, omega here. So we use omega minus omega 0, and then times the amplitude. So this signal can be represented by this one. So that is called the frequency domain representation of the signal. Time domain signal and the frequency domain signal here, they refer to the same thing, right? The same signal. But they have different waveforms in time and in frequency. But they are related mathematically. Right? From again 323, we know they are related by Fourier and inverse Fourier transform. Right? So if we are given the ft function in time, then we multiply by e to the j omega t, then we do the integration with one period and divided by from negative infinity to positive infinity. Right? This one here, and this gives us the frequency component. Right? So we convert a time domain signal through Fourier transform into a frequency domain signal. Similarly, if we are given this frequency domain signal, if we are given this, we want to obtain that one. So that's why if we given this, then we multiply by e to j omega t. The integration again for all frequencies and with respect to the frequency. And this one will give us a ft mathematically. But for some reason, and we are going to divide it by 2 pi to make this consistent. So we divide by 2 pi here. In this class, we do not want to test you how to do this Fourier transform or inverse Fourier transform. We only need to understand that for the same signal, no matter it's in the time domain or in the frequency domain, they are related and they can represent it by both in time and in frequency. Right? So these two signals are the same thing. Right? One is in time, one is in frequency. Any questions on this? This part are just a review of 323. Right?
They should have cleaned the board.
Right, next one topic is the power and energy. Energy and power. If we are given a signal, for example, ft, this signal can be complex, like this one. Can be complex, real part, imaginary part. How to calculate the power? The power is the ft times ft complex conjugate. Then do the integration. Then that one equals the power. The energy we call E equals this one. And again, the integration is for all the time. Usually the signal is not complex. For example, it's real. In real, then ft will be equal to f complex conjugate. Right? So the real signal, for example, 3 plus 4j, that complex conjugate equals 3 minus 4j. So that's complex, and that's complex conjugate. If the signal is real, only 3, this particular 0, then that complex conjugate still equals 3, because this one here is 0. Right? So if ft is real, then ft and ft complex conjugate will be the same. So then this ft squared then dt. For a special case, if ft is a sinusoidal function, omega t, this, from the circuit analysis, we deal with these signals, right? So the input voltage equals V0 times the cosine omega t. Then we plug this one into here, we know the energy will be equal to V0 and squared divided by 2. So that is the mathematical representation. Right? In circuit analysis, we know the energy on the resistor will be equal to the voltage squared divided by 2R. Okay. Right? But we can consider this one as the R is a unit. So you just use 1A or 1 ohm. Okay. So any questions on this part? Again, this one is like in AC circuit. Right? The next one is the power. So what is power? The power is the energy per unit time. Right? Alright, so what we do is here, this one equals, and we do this power Ft times Ft complex conjugate dt. And this time we are going to evaluate on one period, so half t to positive half t, periodic signal, and divided by the length, the wavelength. The period. This is for periodic signal. If the signal is not periodic, we can still consider it as a periodic signal, but the period equals infinity. So in that case, we are going to take the limit when t approaches infinity. So that works for no matter periodic or non-periodic signals. Again, if the signal is real, then this one will be equals this. So that one will be equals limit t goes to infinity, 1 over t. Then from, in that case, we can write this. Or, if you like, you can from 0 to t, doesn't matter, right? The integration is only within one period. So no matter where you start, where you stop, just the length must be equals one period. So we can use this one. Then ft, because this one equals this for real signals. So square then dt. So these are the power of the signal. These are energy of the signal. This is the power of the signal. So later time we are going to calculate if you are given AM signal, FM signal, we are going to know what is the power or what is the energy of both modulated signals. The next topic is trigonometry series of impulse rectangle pulse train. The rectangle pulse train, for example, is like this. There are pulses, and so they are periodic signal. This is periodic signal. We can assume this one here is 0. Then we have another one all the way to the left, and this one all the way to the right. And in this plot, we assume the duty cycle equals 50%. That means this length equals this length equals this length equals this length. Duty cycle equals 50%. And from a Fourier transform, we know any periodic signal can be represented by a combination of thin and cothin functions. So that impulse, for example, PT, impulse, the signal, will be represented by a series of cothin and thin functions. So first one, we have a AC component. We have a DC component. Then we plus a sum of all the n omega t cothin functions. Then plus the sum of all the thin functions. And this n will be equals 1 to infinity, and this n equals 1 to infinity.
What is that?
Which one?
That n over what? Keep going.
This is a cosine n times omega t, like this. This one is a bn.
What's that before that? Bn.
This one,
Epsilon.
this is a, and this one,
Epsilon.
Okay.
this one, this is the summation.
Okay.
Right? This is epsilon, yes, means summation. Right? Sum for n equals 1, all the way to infinity. That means a0 plus a1 cosine 1 omega t. Plus A2 cosine 2 omega t plus A3 cosine 3 omega t all the way to infinity. And same thing here. Okay? Now how to calculate this one? The physical meaning for this one is the DC component. So for this signal, duty cycle equals 50%. What is the DC component? for this signal. For suppose this one equals 0 here, this one equals 1. What's the DC component in this signal? Equals half, right? And because you think like this, okay, cut and move this part to here, this part to here, this part to here. So that like equivalent to a DC signal, the amplitude equals half. And we assume the duty cycle equals 50%, yes.
So is that saying P is equal to A0 plus the summation of AN?
This one here is the post train. In post train means in time domain equals all this is everything.
And is that saying that that whole equation?
Yes,
right there
equivalent to the whole thing here.
Okay, so that A0 plus the summation of AN cosine and
N omega t.
Is that saying that's equal to the summation of Bn sine and omega t to the right?
Let me write this one. Okay, so this time domain, this extend to infinity will equals A0 plus A1 times the cosine N omega t, right? Plus there's another term A2 cosine 2 omega t plus A3 cosine 3 omega t, and we have infinite terms.
Right.
Alright? And this part is also plus here, then plus the first term is B1 sine 1 omega t.
That's a place?
Yeah, see, that's what I was concerned.
This is the plus,
I
yeah.
thought
I
that
couldn't
was
tell if that was
minus.
multiplication.
Oh, this is plus, this is plus, right? And also plus B2 sine 2 omega t, then plus all the terms here. Alright? And the task for us is to evaluate this A0, A1, A1, A2, A3, B1, B2, B3. Right? And also this omega. Right? The omega, what is omega? Omega, okay, this one is the period. So the period is from here, 0, this one. This is the t, right? From here to here, that is the period, periodic signal. Right? This is the length equals t. So this omega, where omega times t equals to pi. So if you are given this time domain signal, you know this t, then you can determine omega, because omega times t equals 2 pi. And what is A0? A0 is the DC component. The DC component means, right, we do the evaluation, and this original signal PT and DT, right, then divided by over t. So that's the DC component. And what is AN? AN, N equals 1, 2, 3. Right? This one equals again integration 2 pi 0 to t, and this PT times the cosine N omega t dt. Then divided by, I believe that's divided by times 2 over t. So this one here. We know omega. Omega is determined by here. Then we can plug n equals 1, then you do this integration, you get A1. You let n equals 2, do this integration, okay, you get A2. And the same thing, Bn equals 2 over t, then integration here, that will be pt, then times the sine function, n omega t, then dt. Right. Again, this is a review. I don't want you to calculate this, but you need to understand. If you are given time domain signal, we can easily use the Fourier transform to calculate all these coefficients. That means this signal can be represented by the sum of all these signals. Now let's see what the sum of all these signals look like. We said equal. That means the sum of all these must be equal to exactly this rectangle question. Let's see what we have. The first term is this A0. So the first one is like this. That's the first term, right? The second term will be calculated for this one. The result actually is given. I will write this one. For this example, the result will be equal to half plus 2 over pi times cosine omega 0 t and minus 1/3 cosine 3 omega 0t, then plus 1/5 cosine 5 omega 0t, then minus 1/7 cosine 7 omega 0t. Like this. And infinite terms. So you can see this term actually is 0. And the even terms, A2, A4, A6 also equal 0. Only we have 1, 5, 1, 3, 5. Okay, so now this one we draw this. The first term is half, that is half. The second term is cosine omega 0t. Omega 0, because t equals 1. So omega 0 will be equals 2 pi, right? Because these two multiplied together equals 2 pi. So the first cosine term is look like this. Like this. Right? That's the first cosine term. So we have this, we have this. The next one, 3 times the frequency. So it will be like 3 times. So this one here is 1 cycle. We need to have 3 cycles. 1, 2 here. So it will look like this. 1 cycle, 1 cycle, 1 cycle. And this one the same thing. Alright? Like this. Then 5. This one is here. 5. Even higher frequency. And the amplitude decreases. Smaller and smaller. So add all this together, it gives you like this. That is what you can. There's a homework question problem let you to practice this one. You can draw this. The formula is given like this. This is 1, negative 1/3, 1/5, negative 1/7, 1/9, negative 1/11, and so on. You calculate this one, you add all these terms, you plot this, no matter use what kind of software, right? And you will get all these sums, the sums of all these functions will equal to very close to this rectangle question. You are going to discuss, for example, if you use 10 terms, what you get? If you get 50 terms, what you get? Try to find out the relationship between this. Okay, any questions on this? So this is the homework. Right? You don't need to calculate all this coefficient. The coefficient is in the homework is already given. So only what you need to do is you only plot like this, but with a perfect, not like this mess. Right? Next topic is decibel. And in circuit analysis, we deal with, for example, gains attenuations. The number may be very large, like 10,000, or very small, for example, 10 to the negative 6, small numbers or big numbers. In that case, we prefer to use decibel instead of the absolute value. So what is decibel? Decibel usually applied to a ratio. So that one usually applied to a ratio. The definition is the dB value of a ratio, for example, V1 over V2 is the ratio. If you are given this ratio, how to convert it into dB? Suppose we use P1 and P2. P1 and P2. So what we do is we take the log base 10, then multiply by 10. That's it. You are given the ratio in power, then you take the log base 10, then you times 10. That's it. And sometimes the ratio is in voltage, not instead of power. For example, V1 over V2, like this. And we still take the log, but we need to multiply by 20. The reason is P1, P is proportional to V squared. So if you replace this P with V squared, so you can see that squared here, this 2 must be moved to the front, so that will be 20. Similarly, if you are given in the ratio of current then you still take the log of this 10, then multiply by 20. Like this. Okay, now let me ask several questions. Suppose the gain equals the power gain. The power gain. The power gain A equals 100. What is this converted into dB?
100 log base 10.
Okay, 100 log 100 base 10 equals what? Equals 2, right? You take the power, then multiply by 10. So this one equals 20 dB. Make sense? Alright, next one, for example, the gain equals half. And what is this? You take the log of half of base 10, that give you negative 0.3. Then times 10 give you negative 3. And negative 3 dB. Alright, now you may remember this. Alright, we discussed the circuit analysis, the 3 dB bandwidth. That means the bandwidth where the amplitude reduced from the 1 to the half in terms of power. So that is the bandwidth. That is the definition for 3 dB bandwidth. Alright? Any question on that? Alright, so this is a power gain. How about if the voltage gain? For example, you have amplifier. The input equals 1 volt, the output equals 100 volt. So the gain equals 100 over 1, which equals give you 100. Again, the gain equals 100. Convert this one into dB. The voltage gain equals 100. How many dB is this?
40.
40, perfect. Okay, 40. Okay, now I ask you another question. Okay, well, I need to discuss something first. We know the power, the unit of power is what is the unit of power? The unit of power is what? Watt, right? And sometimes we do not use this one. We can use a dB watt. So what, for example, so this power equals 0 dB watt. What does that mean? That means it is your power in watt, in watt here, divided by 1 watt. Why divided by 1 watt? Because we are talking about the watt here. So divided by 1 watt. Then you take the log base 10, then you multiply by 10. So this value give you dB watt. Does this make sense? Okay, so for example, I said the power to the transmitter equals 0 dB watt. How large is the power? So, okay, 0 dB watt. How large is the power in traditional way, in the watt? How many? 0 dB watt equals how many watt? Equals how many? Okay, we don't know here. That one is this one. You use this number here divided by 1 watt. You take the log of base 10, you times 10 equals 0. So what is this one here? This thing divided by 1, take the log times 10 equal to 0. What's this? This equals 1, right? So this one equals 1 watt. Right? So 1 watt, suppose your power equals 1 watt. If 1 watt divided by 1 watt, that ratio give you 1, right? You take the log of base 10 of 1, which you get 0. 0 times 10, still get 0. So, because 0 not watt anymore. It must be dB watt. That means that is 0 dB compared to 1 watt. That make sense? Okay, good. Okay, next one, you may want to use a dB milliwatt. So anyone knows this definition? You know this, you should know this, right? So what is dB milliwatt? So that one equals 10 times the log base 10 of your power divided by 1 milliwatt. Alright, so now let's give you ask question. 0 dB watt equals how many dB milliwatt? What's this? 0 dB watt equals how many dB milliwatt?
0.1.
0.1. Okay, let's try. We know this one equals how many watt?
1 watt.
1, alright? It's 1. So this power P equals 1 watt. So we plug this P into here, right? So 1 watt divided by 1 milliwatt. What's that ratio? 1,000. You take the log of base 10, give us 3, right? 1,000. 1,000 means 10 to the 3. Take the log of base 10, you get 3, right? So 3 times
30.
30. So times 10 equals 30. So this one here equals 30. So 0 dB watt equals 30 dB milliwatt. Is it good? Alright, now let's continue. How many dB microwatt? Right? You should understand this micro, right? Means
60.
dB compared to 1 microwatt. So what is the
60.
number here? 60. Perfect. That's 60. Alright? So now you can see the relationship between watt, dB watt, dB microwatt. Right? dB, this one is 30, 60. So suppose usually is multiplied by 10, 1,000, 1 million. Now you just add 30, add 60. Why we want to use this dB concept? We can convert a multiplication into a addition. We can convert in a division into a subtraction. Right? Give you another example. You have a cable TV at home, right? So suppose this one you have this is the input, right? From the wall, right? And this one, the level, the power level, for example, is negative 40, suppose, right? Make some number. dBm. dBm, if we mean dB micro m watt, okay, we can ignore this watt. Right? dBm means dB milliwatt. Right? If you mean dB voltage, then you need to write this one. Right? Only for power, you can ignore this. So that means negative 40 dB milliwatt. That's the input power from the cable company to your home. Now you have 2 branches. It means you have 2 TVs connected to this one. So one TV1, okay, TV2. You use this is called a divider. 2 divided by 2. You want to divide this power equally into 2 parts. So my question is, what is the power here? This is negative 40 dB milli. What is the power here? These 2 must be equal, right? Yeah? What is this? Alright, now I make this easier. Right. Suppose this one equals 0 dBm. Now you divide it by into 2. What is here?
Oh, 0.5.
Alright?
0.5 watts.
Very close. Okay, so this one 0 dB means equals 1 milli, right? 1 milli divided by 2, so that's 0.5. But we are not interested in 0.5 watt. We are interested in dB.
15, it'd be 15,
So negative half. I think we have some here. This is half, right? Half means negative 3. We suppose to divide it by 2, right? So that's divided by 2. Then we said division converted into subtraction. So you suppose to use 1 divided by 2. Now you are going to use 0 because 1 equals 0, right? 1 watt equals 0 dB watt. You divide it by 2, then you subtract, not 2, 3. Right? So using minus 3. So that's why here we have a negative 3 dB watt.
So both on -3.
So this one here, both will be negative 3 dB. So 0 in, you get a negative 3 here, negative 3 here. It's good? No? Alright, now look at this one. Negative 40. What do you have here? Again, as you said, divided by 2, but in dB we need
yeah.
minus 3, right?
-43.
Yes, perfect. So negative 43 dB. What is here?
Same thing.
Same thing, negative 43 dB. So negative 40 divided into 2, you get negative 43 each.
That don't even make sense.
Doesn't make sense.
you know?
That don't even make sense.
Keep in mind, there's a log here, right? Make a lot of sense. Right? Spend some more time here. Okay. For engineers, technologists, you need to feel very comfortable about these conversions. Right? So you, for example, you have some the power. Okay, how about divide by 3? And you have 3 branches like this one. This divide by 3.
It'd still be -3.
That'll be divided by
Like third, it ain't divided by 2.
So it'll be 1/3.
1/3. Yeah, use this way. It is 1/3. 1 divided by 3 is 1/3.
So
But to use a dB, you minus what?
So the number gonna go down.
So you need to take the log of 3, that times 10. I think that is negative 4.7 something. So about 5. Negative 5. 4.77, I guess, right? So that one will be negative 45, negative 45, negative 45. Yes.
So however many times you're trying to divide it, that's what you do the log of times 10? That's what you're talking about?
Every time you
get what I'm trying to
divide, you need to take the log and then you subtract.
Like I'm saying, if you were going into 5 different things, you'd get the log of 5 times 10? That's what you're trying to say?
Yes.
Alright.
Does that make sense? No? Not at all?
Yeah, it makes sense.
Huh? Make sense? Okay, good. Put some more time here, right? And you need to be very quick on all these conversions. Three dB means half, right? Negative 3 dB means half. Right? 3 dB means double, right? For example, you have a TV, the signal, you want to receive the signal from the air. Right? Your signal, suppose this is your TV. Right? Now you have an antenna here, and you can, okay, suppose you just want to receive the signal to a TV here. And the received signal power equals, for example, 1 microwatt. Just, again, make some assumption. Right? Now you use the antenna. So you have antenna here, then you connect this signal to here, and this value, for example, change into 2 micro. What is the gain of your antenna? Double. Right? So that means that the gain equals 2. The gain equals 2 in the traditional way. So just the ratio equals 2. And no unit base. But when you buy the antenna, they won't tell you, okay, the gain equals 2 or equals 10 or equals something. They give you the gain in terms of dB. So how many dB is this? 3 dB. So that means this the gain of the antenna 2 equals 3 dB. Okay, make sense? So if your gain equals 3 dB, it means you double the signal. If your gain equals 6 dB, that means how many times? 4 times, right? You add another 3 dB, you add another 3 here, you multiply by another 2 here.
Yeah, about 3 dB.
Right? So how about the 9 dB here? How many times? 8. Perfect. Right? Because this one add another 3, that means you multiply 2 again, so 8 times 2 is 8.
No, that's wrong. It should be 6.
This one,
multiply
addition,
by 2,
this
man.
is multiplication.
2.
Oh, that's the.
Alright? So how about the 12 dB?
Now wait a minute.
16.
So what's 6 give
16,
you? What's
right?
6 give you?
Huh?
What's 6 give you then?
6 given equals 4. Because this one you add 3, you
No,
multiply
like
2.
6 on this side.
6 on this side.
Yeah.
6 from here, even here.
Yeah, what's 6 of these?
6 is like 3 plus 4.77 is like 7.77. So this one here, 7.77. It's between this. As I said, 3 means equals 4.77. That's my guess, right? So you add 2 here, you multiply by 6, that's 1.5. So this one may be something like that, 7.7. Right? You just take the log of 1.5, then take the log, then it's 10, then times 10. You add to this. So multiplication in here, addition in here. Addition in here, multiplication in here.
All right, so what would 5 be?
Right?
5.
5.
Yeah.
Log of 5 is 7. 5 is log of 5 equals 6 minus 9. Then times 10, so equals 6. So equals 70.
Hey, we do that part from right?
Huh?
The part, the first part you just did. But
Which part? This part?
Yeah, all of it. How you do that again?
This is 3 dB means 2, right? Right? 0 dB means what?
We just
Oh,
gonna play last
one half.
0 dB means
1.
yes, perfect. 0 dB means 1. Right? Now you add 3 dB means you multiply by 2. You add another 3 dB, you multiply by another 2. You add another 3 dB, you add another, multiply by another.
Add on this side, you multiply this side.
Yes. So that's a multiplication converted into addition. Right? And here, division converted into subtraction. You divide it by 2, you minus it. So you divide it by 2, if you divide it by 2, you minus 3. You divide it by 4, you minus 6. You divide it by 8, minus 9, you divide by 16, you minus 12. So that makes things much easier. You do not need to do the multiplication and the division. Instead, you just use add and subtract. Later time, we are going to use this later. Play this a lot. So make yourself feel very comfortable about all these conversions definitions. Yes.
We be putting lecture notes on the site online.
Do you want the lecture notes?
Yes.
That help out with
Right? I have mixed feelings from you. Sometimes you don't want this one, sometimes you want. Right? If I put the lecture notes on this one. Anyway, so if you want, then I can put on the website. Right? Okay. Any question? This is the little bit math here. Right? So. In electrical engineering, for example, antenna engineering or micro engineering, you need a lot of these dB things too. For example, give you antenna, ask you to measure the properties, right? Characteristics of antenna. So tell me what is the maximum gain. You never tell me, okay, equals 100. No way like that. 100 means if you are in terms of power, that will be 20. It's at 20 dB. Right? For example, stop band You reduce the signal from 1 to like, for example, 1/10 in voltage. You do not say, okay, the gain or attenuation equals 10, or the gain equals 1/10. You do not see that. Instead, you say, okay, the attenuation equals 20 dB, or the gain equals negative 20 dB. Always use unit of dB. Next topic is noise. We have correlated noise and uncorrelated noise. Correlated noise means it's from nonlinear device. For example, we have a circuit here. There are transistors inside. We know transistors are not a linear circuit, not a linear device. It is nonlinear. That means nonlinear means the output related to the input not just multiplied by a constant. This is a linear circuit, right? Instead, it will be a squared, even cubed, even higher. So that's why, if your input signal is, for example, from here, that is 60 hertz, right? Then you are going to have another one, 120 hertz. That is called a second order harmonic. And possibly you have another 180. This is 3 times of this, so that's a third order harmonic. Like we said in the beginning, cosine m omega t, so omega equals 60, this m omega equals 1, this omega equals 2, this omega, this m equals 1, this m equals 2, this m equals 3. So that's the harmonics. Because the circuit is not linear, so we are going to have this. This gives us noise. This is called a correlated noise. That means if you have the input, you always have this noise. You cannot remove this noise because your circuit is not linear. If your circuit communication system operates, then this noise is always there. So that is called correlated. Uncorrelated means not related to this. It's, for example, man-made or external. For example, this is noise. I can stop this. So I do this means interrupt your communication, but I can stop this. So it's not necessary. Sometimes it's called external, or for example, the solar system. And solar system, they have some like a solar noise. Sometimes when you watch the TV, especially if you use antennas by yourself, right? You watch TV, sometimes you can see a lot of snows here. Or maybe your neighborhood has a car passing by, right? Give you a lot of noise. That is all uncorrelated noise, called external noise. Not related to your circuit, to the outside. The next one is in communication system. We have another one, it's called crosstalk. Crosstalk means, for example, you have a cable. Usually this cable has 2 ways, right? Transmit, receive. So this is the transmitter, T and R. This is also T and R, right? Transmit at the same time. You are here. Right? If the noise is from yourself, for example, if you make a call with your computer, sometimes you hear the echo. The echo is from yourself. That is this. You make the transmission, but you hear it, your voice. Right? That is called near and cross talk. If this noise is from here, linked to this part, and come here, this is called far end cross talk. So how to, no matter what this far end or near end, all these are crosstalks are not what we want. We want to eliminate this. So how to do this? Use better cables. Some other ways like use balanced transformers, common mode amplifiers. You know common mode amplifier, right? So in circuit analysis, common mode amplifier, differential mode amplifiers. We all learned this before, right? So now you need to use this part of this. And also another important thing is you want to limit your signal level. If your signal level is very high, very strong, for example, at your home you have internet. If your signal is very strong, you may lose your signal. You cannot connect it to the internet. Why? Because your signal is very strong, like this one. Suppose, just make an example. We are going to cut off, so make some like distortion. Like when I talk here, you can hear, for example, clearly. If I talk very loud, there's distortion in my voice. Because the power is very loud, then this one is not good. Okay? So, in communication system, not necessary the stronger signal, the better. You need to limit the signal. So this is called distortion. This what we just discussed is called over-modulation. Because your signal is too strong, and make some distortions. This one will limit the property of the transmission. For example, if you want to transmit your signal very far away, how can you do it? Everything else is the same. The same channel, the same everything, transmitter, receiver. If we want to transmit far away, I talk to you here, I can just use this voice. If I want to talk to somebody over that building, what I need to do? Increase my power, right? Increase the power, then you have over-modulation. That means the distance will be limited. So what do you do? If you want to transmit far away, you need to use a repeater. So like I talk to you, you talk to that one talk to, okay, so you can do this, use a repeater. So give us an extra cost. If we have some way that can overcome this over-modulation, then that will be best. Right? There's a paper published on Science in 2015. It's researchers in UC San Diego. Right? They invented some method that can transmit the signal from an optical fiber for up to 7,000 miles without any electronic repeater. So that is very good. Okay, any question on this? We discussed a lot of noise, but what we can calculate in this class is the thermal noise. The thermal noise is calculated, the thermal noise. The power of thermal noise is N equals KTB. K is called the Boltzmann's constant. This one equals 1.38 times 10 to the negative 3. T is the temperature in Kelvin, in K. And this B is the bandwidth in Hertz. So the larger the bandwidth, the higher the operating temperature, the larger the thermal noise. For example, a typical communication system, the bandwidth equals maybe, for example, 30 meg, suppose 30 times 10 to the 6. The T will be like, for example, room temperature. That will be like close to 300 Kelvin. Then we multiply by 1.38 times 10 to the negative 3. Look at this. How small is this number? This is 6, this is like a 6, 7, 9, 10, right? 6, 7, 8, 9, and there's 3 here, almost 10. So that's almost 10 to the 10. Right? 10 to the 10, there's a 1.3 here, then times 10 to the negative 23, so this is 10. So we combine together, it's almost negative 13. Right? That is the watt. So you can see the thermal noise power is very, very small. And again, we don't like this small number. What we can do is the dB value, right? So the dB is about negative 130 dB watt, right? Negative 130. So you should be very quick on this calculation, right? Almost like very close to negative 130. Negative 130 dB watt. But sometimes we want to use another concept. We want to use the voltage, right? So Suppose you have a like this. This is your system. This, if we consider this one as your source of the noise. This source of the noise applied this noise power to your communication system, to the load. Suppose this load, the voltage, the resistance equals R. We want to know what is the voltage here. Okay, we use Vn, the thermal, the noise voltage. What is this? Can give us this kind of power. In circuit analysis, we know if this is the source, and we know there's an internal resistance here, when this load can get the maximum power. When the load equals the internal resistance, right? Or the voltage here equals half the voltage here. Right? Based on this rule, so the power KTB will be equal to, because when this equals this one gets the maximum power, so that is the worst case. So this voltage will be equal to half of this Vn. So Vn over half, that's the voltage over here. Then V squared divided by R. That gives us the power on this. And we assume this power is provided by the thermal noise, which equals this. So from here we get Vn equals, so that is, so KTB times R, then times 4, then take the square root. So this is the thermal voltage, equals 4 times R times TB times R. This R is the resistance of your system. Right? So if you plug all these numbers, this one equals 300 as this one equals 30 meg, this one, for example, equals 100 ohm or something, then you take the square root. You are going to get this one is about some microvolt or even millivolt. So in this level. So this number is much, much larger than this one. It's easy to deal with. So usually the noise voltage will be equal to some like microvolt or millivolt. So sometimes we use this one. We said, okay, this system has a noise voltage of this. That means that this voltage as the source here will give the same thermal power. Now we have next one is a signal to noise ratio. Signal to noise ratio. That's easy to understand. You have a signal. You have the power of the signal. You have the noise power, and the signal power divided by the noise power equals the signal to noise ratio. That's it. But again, sometimes we said we know this one is small. This one usually compared is large. So this number is large, right? So we are going to use the dB concept instead of this absolute value. Right? So what we do is in dB, just PS over n, and take the log base 10 times what? Times 20 or times 10? Times 10, right? Because we are talking about power, so times 10. So that is called the signal to noise ratio. Alright, now suppose we have this communication system. You have input, you're going to have output. Right? At the input, this is the signal. The signal has a noise. So we have a signal to noise ratio at the input. Right? At the output, we also have a signal. We also have noise, and so we have signal to noise ratio at the output. Which one is larger? This one or this one? Right? This one is larger than this one. Because this system can only make the additional noise, make the things worse. You cannot make this one better. Right? And we have a definition. It's called noise factor. Noise factor, represented by F, is defined by the signal to noise ratio at the input divided by the signal to noise ratio at the output. So input, output, both have signal to noise ratios, and the division, the ratio of these two, input to the output, equals noise factor. So F. Now we have a very simple system. Suppose this is just a linear amplifier. Right? So we know the gain equals A, and we have additional noise. We have additional noise N. So at the input, we have a signal, input signal. We have an input noise, and we have gain here. We have additional additive, and that is added to the signal. So this is an additive noise, and we have an output signal power, and we have an output noise. Yes.
Where you have the signal noise ratio equal to PS over N and then 10 log base 10, is that also PS over N, or is that V?
This is PS over N. It's the power of the signal.
Okay, so, but it's over N?
Yeah, divided by N. N is
That's
the power of the noise.
Okay.
And so power divided by power. Signal power divided by noise power.
Okay.
Signal power divided by noise power ratio. Okay, so this is the system, very simple. This is the gain of A, additive noise. This one, at the input we have Si, Ni, at the output we have the S output, N output. So let's see what this is, this F. The definition is this. So the F equals the signal to noise ratio at the input. Let's see which one is first. SNR at the input equals Si over Ni. That's the definition here. And SNR output equals the SO over NO. Again, this is the definition. So what is this? SO, the output signal, equals the input signal times the gain. That's the linear amplifier, right? And the output noise equals the input noise, also you need to multiply by this A, by the gain, right? But we have additive noise here. Right? Now, we have this, and we use this one divided by this, we get F. So that F will be equal to, you do the math, very simple, equals 1 plus A and N, A, and I. So the noise factor equals 1 plus additive noise divided by A divided by input noise. So we know A is positive, right? The gain always positive. The noise power are always positive. So we can see this one is always greater than 1. So you can, any system can only make signals quality worse. You cannot make it better. How about the equal? I do not make the signal worse. Can I do make this equal? Equal means this F must equal to 1. How can you make this F equal to 1? This is positive, positive, positive. So look like this one must be positive. It's greater than 1. So how to make this one equal to 1 means make this one equal to 0. How can I do that? Either way, you can make this A equals infinity, right? So your gain of your system equals infinity. Can you do that? Not easy, right? Right. So there's no way. Input noise is always here. The another way is you can make your additive noise to 0. That means your device, like resistors, transistors, have no noise at all. Is this possible? No. Why? Because see, your system operates at some temperature, right? Here, 300. Have some bandwidth, right? You need bandwidth, otherwise, what is it? Nothing. Not, you cannot communicate anything. So this one, all positive. So this N must be positive. So you cannot make this F equal to 1. Can only be greater than 1. Except you want to make this T equal to 0. Then the noise equal to 0. How can you make the T equal to 0?
Super cold.
Super chill.
Super cold, right? Where? liquid nitrogen, that is negative 23, something, or close to 0, right? But still not equal 0. You may want to move your communication system to outer space. Right? Don't laugh, okay? Scientists already done this. They try to make this, they want to detect the micro, to detect aliens. So they need to receive signal. These signals are very weak, so they cannot make this noise loud. So what they do is, they make this one very, very low, right? So that's possible. But for us, no way. You can only operate this one in the room temperature. So this one is for one stage. How if you have several stage like this? This is 1, this is 2 or 3. The system you connect it all together. So suppose this one equals F1. This system has a noise factor F1. This one has F2. This one has F3, and so on. We have a lot of communication system cascaded together. What is the total? The total, you derive this with the same formulas. It's complete lengthy, but I just give you the result. F1, the first one, plus F2 minus 1 divided by the gain of here. Then plus F3 here minus 1, then divided by the gain here and multiply the gain here. Then plus F4 minus 1 over the gain of here, then times the gain of here, then times the gain of here. So usually we see the gain is greater than 1, right? Usually. So you can see this one is smaller and smaller, smaller. So the major contribution to the whole system is the first stage. This one is smaller because we need to divide it by the gain. So this one, the contribution is smaller. And this one is even smaller. So later time we can just ignore. That means when you design a communication system, you want to put your best system at the very beginning. Best system means the noise is very small. The noise factor is very small. You put your best at the front, your worst at the very last. Because the contribution at the very last is supposed to be divided by all these gains. So it's very small. Remember when you design pre-amplifier, you need to think about when you design pre-amplifier. Why you want a pre-amplifier? First one is impedance matching, right? The next one is for this quality. You want the best device to be in the pre-amplifier. For example, you want to spend more money to buy the better resistors, transistors. Better means the noise is small. Sure, it costs more. So you want to make this one small, then your system, the total system can have smaller. This one. Okay, so you see it here. We have a last line. Information capacity. For example, you have a communication system. We know we have a signal-to-noise ratio. We have a bandwidth. So how much information can you transmit? The capacity, the transmission capacity, will be equal to proportional to the bandwidth. The bandwidth times the log base 2, then the signal-to-noise ratio plus 1. You have a system, right? So you have a signal-to-noise ratio. You plus 1, you take the log times base 2, then times the bandwidth. That is the maximum information you can transmit. For example, for your cell phone, suppose this one equals 30 megahertz, the bandwidth. This one suppose equals 40 dB. So how much information, how fast can you transmit with your cell phone? Let's see, do this. 30 meg here, and times log base 2. This is 40 dB. We cannot use dB. We need to use the absolute value. 40 dB equals 10,000, right? Yeah, okay, 10,000, 10 plus 1. Right? Okay, so this, you take the log of this one. Right? This one is about 13 something, because the log of 1,000 equals 10, then plus another, times 10, then plus 3, so approximately 13 something. Then times 30 meg. Right? This one will be equals about 400 megabit per second. So that means use your cell phone, at most, you can transmit 400 megabit each second, per second. That is the capacity you can transmit. You cannot transmit faster than this. In real life, you will transmit much, much slower than this, but that is the maximum. Because there are some other factors will affect this transmission. This is the maximum. This is called the Shannon's theory. The last topic is called the bit error rate, BER. We just mentioned this. Bit error rate. Bit error rate. Yes, for example, I transmit with this speed, suppose, right? So in each second, I will transmit 400 million bit signal. Because some errors. So for example, there are 400 bit are wrong. When you receive this, 400 bit are distorted. I transmit 1, you receive 0. I transmit 0, you receive 1. And this 400 bit are wrong. But you totally transmitted 400 megabits. Right? The error bit, the number of error bit divided by the total transmitted, that is called the bit error rate. So in this example, that one equals negative 10 to the negative 6. So the higher the quality, the smaller the bit error rate. If your transmission situation is very bad, then your bit error rate will be large. For digital phones, everybody has a digital phone. You don't have any analog phone anymore, right? Who has any analog phone? No one, right? This one, the good thing is if your signal to noise ratio make this one small, then the quality is perfect. If this one is your signal to noise ratio reduced to make this one more than a threshold, you receive nothing. So if I draw this, it's something like this. This is digital. Analog, like this one. Or we can say like this. Analog means there's a lot of analog code. You can still listen to it, right? But for analog, for digital, you just receive nothing. If the signal is too bad, then you cut off. You drop the call. For analog, you can still make noise, right? Like in the war, in the battlefield, you can still listen to it. But there's a lot of noise, like this. So that's the difference between analog and digital. Okay, I think that's it. There's another concept, it's called noise power density. Noise power density, which is equal to KT. That's nothing, you can illustrate this. Okay, that's it for today. The homework, you know the homework, right? Website, you can see the homework is due.
It's online.
It's online, yes. Okay, thank you.